Greetings, physicists. This video will be about how to solve problems involving simple harmonic motion, and we'll be focusing on the sinusoidal nature of simple harmonic motion. So, start off with an easy one. We've got a radio station, and this is probably true that there's one that broadcasts at 100 megahertz, and we're just looking for a period. So, pretty straightforward. They give us frequency. Frequency equals 100 megahertz, and we're looking for period, and we know period equals 1 over frequency. So this is just kind of a plug-in. Main thing is that you have a mega in front of the hertz, so we've got to convert that to regular hertz, or we won't get seconds. We would get something like microseconds. So let's do this. We have 100 megahertz. If you didn't already know, mega means a million of something. So 1 megahertz, if we're canceling, goes on bottom. And that's a million hertz, or 10 to the 6th hertz. And we've already got 100, so that's going to be 2 more tens. So really, when I plug this in up here, it's going to be 1 over 10 to the 8th hertz. Okay? And 1 over 10 to the 8th hertz, well, just flip the 10 up to the top and make it a negative 8, so 10 to the minus 8. And 1 over hertz, so 1 over hertz. Well, remember hertz. A hertz is a 1 over seconds, so that's 1 over seconds, or just seconds. So 10 to the minus 8 seconds, or 1.0 times 10 to the minus 8 seconds, because this is a 2 sig fig problem. We want to indicate that. We can clean this up if we want. That's also the same as saying 0.1 times 10 to the minus 9 seconds. And a 10 to the minus 9 of something is a nano, so this is 0.1 nanoseconds. You could also go the other way if you wanted to. If you wanted to change this to like a 10 to the minus 6, you could add 2 zeros. So this is 100 times 10 to the minus 6 seconds, or 100, 10 to the minus 6 is a micro of something, so that's 100 microseconds. So these two things are equivalent. And technically this, well, no, technically this is not correct. You would, if you were going to leave it in scientific notation, you would leave it like this. So, not this one. Also with the 100 microseconds, you would want to indicate that it was a 2 sig fig problem. If you do the 0.10 nanoseconds, just including the 0 lets everybody know it's 2 sig figs. Okay, let's keep going here. Okay, glider on a spring. We will actually probably do this lab. We are given frequency. We are given amplitude. So we have frequency, amplitude, and we're looking for a position after a certain amount of time. Whenever they give me a time like this and say where does this thing end up, I mean, there's a couple of ways that you could try to solve this. One thing I'm going to check right away is how close is the frequency. Is the frequency a factor of the period? So remember, frequency equals 1 over period. So if it has a frequency of half a hertz, then, well, actually, I'm going to have to flip that around. T equals 1 over f, so that the period would be 1 over a half, which is 2. So the period is 2 seconds. That's convenient because it's a multiple of 1. And so where will the glider be 1 second after its release? Well, it will have gone for half a period. So that's easy to solve by drawing it and doing a visual thing. So let's look at the glider. If you had a glider, so this is like a low friction track. In fact, it's like an air hockey table essentially. Little jets of air are going to keep this thing off the ground. It's attached to a spring, and the spring will be attached to something like a wall. And we are displacing it. Let's say equilibrium is here. We're displacing it by this distance, this 12 centimeters. Now, a period of 2 seconds means that if it starts at 0 seconds, it will go here and back. So it will it will complete one full oscillation and return to where it started in 2 seconds. Well, half of that motion means it got to here. So if equilibrium is here, it went to the other side of equilibrium, which is minus 12 centimeters, which is where it should be after 1 second. It should be half of the way, because you can divide this up into 4 equal periods of motion. There's the start as 0. After a half a second, it would be here in the equilibrium position. After 1 second, it would be here. After 1.5 seconds, it would return back to equilibrium, and after 2 seconds, it would be back to its starting point, which is the positive amplitude. Did they give us a right and left on this problem? Suppose the glider is pulled to the right of its equilibrium position by 12 centimeters. Where will it be 1 second after the release? It will be 12 centimeters to the left of its equilibrium position. Then it says, what is the velocity? Now, there's another way to do this, and I'll show you that way too. You can do this with a sinusoidal function. Remember, the position as a function of time should be the maximum amplitude, A. It's a cosine function, right? Because we start at maximum amplitude times the cosine of 2 pi t. And we're either multiplying by f or we're dividing by period. And they give us f in the problem, right? If you go up, you see the frequency was a half a hertz. So I'll just go ahead and do 2 pi t times f. And so what I'm really plugging in to see where my position will be at some time t, I'm plugging in the amplitude, which was 12 centimeters, which I'm going to make 0.12 meters, okay, times the cosine of 2 pi. The time they gave me was 1 second. After 1 second, where will it be? So let's keep that in there. And the frequency is half a hertz. Now I know it's half a hertz, but remember hertz is a 1 over seconds. Check that out. Seconds will cancel. All right, and I will get a position in meters. So if you put this into your calculator, 1 times a half should be a half, right? And then a half of 2 is just, right? So we're just doing cosine of pi. And multiplying that by 0.12. And you're going to want to be in radians for this, whenever you have a pi in there. Okay? So, if I take the cosine of pi, I get minus 1, and I have to multiply that by 0.12, and sure enough, we get minus 12 centimeters. So, this also works. Now, the second question says, what is the velocity at this point? Well, again, we can solve this 2 ways. If we go to our picture, at the edge where we started, we released it, and we released something from rest, right? If you pull it to there and let it go, we're assuming that it's at rest at max amplitude. Well, when it gets to this side, it's at max amplitude on this side. It should also go to rest. That's the farthest it goes before turning around. So at the turnaround point, we expect the velocity to be 0. But we can confirm this, assuming I can scroll here. Remember our velocity as a function of time. Same equation, but instead of a cosine, we have a negative sign. So this is minus the velocity max times the cosine, times the sine of 2 pi ft. Now we don't know the maximum velocity. We could probably calculate it, but watch what happens here. This is inside of the parentheses. The sine is going to be 2 pi. The frequency, again, was a half a hertz, and the time was 1 second. So that's a half times 2 is 1 times pi. What's the sine of pi? The sine of pi should be 0 if you're doing it in radians. Remember, do these in radians. Sure enough, I get 0. So it doesn't matter what the maximum velocity is because I'm multiplying it by 0. There you go. And so two different ways to get the answer to that problem. I personally prefer the picture approach, but if you're more mathematically oriented, you might prefer the other approach. And then on a test, of course, it really depends on what I give you. Okay. This is an interesting thing that I never thought about until I took physics, which is that buildings sway back and forth. The building you're sitting in is swaying back and forth. It's probably not going very far. Sometimes it's so slow and the amplitude is so small that you don't notice it. In fact, I would say for most things. When they're really tall buildings like this John Hancock Center, it can be observed, and they can put cameras on them and measure them, and especially when you have big wind. So if you're an engineer, you have to build buildings that can withstand that kind of oscillation, which is an interesting effect. All right, what are we looking at here? We're looking for speed and acceleration. Okay. Let's see here. John Hancock Center is 100 stories tall. Strong winds. We have an amplitude, it looks like here, 40 centimeters, and we have a period. So it looks like we're going to be able to use our maximum speed and maximum acceleration equations, right? So we had that Vmax equal to 2 pi frequency times amplitude, and that Amax equal to 2 pi frequency quantity squared times amplitude. Now the only issue I have is that this is a period, not a frequency. So this is 2 pi a over t, and this will be 2 pi over t squared times a. So let's do the velocity first. Velocity max is going to be equal to 2 pi. The amplitude was 40 centimeters, or 0.40 meters, over t, which was 7.7 seconds. Let's see what the calculator says. 2 pi 0.4 divided by 7.7, 0.326, which is not very fast, about a third of a, and I think it's a 2 sig fig, so 0.33 meter per second, third of a meter per second, not even walking speed really. And the acceleration max will happen at 2 pi over 7.7 quantity squared times that 0.4. Okay. 2 pi divided by 7.7 squared times 0.4. Okay, and that's smaller, or smaller magnitude. And if I round that to 2 sig figs, I get 0.27 meter per second squared. A fourth of a meter per second squared. All right. So that's fairly straightforward. We just had to change an F into a T to make that work. All right. Hope this helps you out in solving simple harmonic motion problems.